Okay, so in this video, we're going to talk about how to determine limits analytically. So that means we're not going to need a table or a graph to determine the value of a limit. So we're going to go through a couple of, just a variety, some different examples here. This first one here is a very simple one. So we're trying to figure out what does 6x squared plus 3 approach as x approaches minus 1. So when you look at this one, this function has no strange behavior or discontinuities anywhere near -1. So this one we can get by direct substitution. So if you want to calculate this limit here, you can just let x be -1. Okay, so all we're doing here, just direct substitution, so we put -1 in place of x, and this will be your limit, right? So this will be 6 times 1, so you'll end up with 9. So this is the simplest scenario, almost not worth doing, right? Because it's really telling you that the value that this function approaches is actually the same as the value where it arrives, right? So in this case, the limit is equal to 9. Okay, so naturally not all examples are going to look like that. So we're going to move to something a bit more challenging, right? And this might remind you of some of the other ones that we saw when we were looking at tables. So when you look at this example, you might want to try the exact same thing, right? So we would just say x is approaching -3, so why don't we just insert -3 directly into this function and determine what happens. So you can see directly on the bottom, -3 is going to cause a problem, right? It's going to give us division by 0. And if you look carefully in the numerator, we're going to get positive 9 plus 3, which is 12, right? 12 minus 12 is equal to 0. So this is a pretty common form in calculus. We have an indeterminate form, so it tells us you can't determine this limit by letting x equal -3. You have to devise a technique for determining what this function is doing close to -3. So we'll go through some of the mechanics here. Okay, so the limit here is x approaches -3. What we can try to do is to factor the numerator. Okay, so we'll use our regular techniques here. And obviously you can go back and make sure you understand all of this. Okay, so we're just going to decompose the quadratic into these two factors here. And so the thing to look out for now is you'll see a common factor of x plus 3. And notice here that x is approaching -3. So because x is never equal to -3, it's valid to cancel out these factors, right? So we can remove these, and so we're just looking at this function here. So this becomes the limit as x approaches -3 of x minus 4. And now if you look at this new problem, the thing that you gauge from this is this becomes like the older problem where this function has no discontinuities and no problems. So you can let x equal -3, right? Direct substitution. So here you'll just get -3 minus 4, and this becomes -7. Okay, so the comment here that's important is, again, you can't let x equal -3 into this function because we already know what happens there. But what this statement is saying is you can let x get very close to -3. And this is what you can expect to see, right? Numbers that are very, very close to -7. So that's related to some of the earlier things that we talked about. Okay, in the earlier lessons we did talk about making tables or looking at graphs. So I'd just like to demonstrate this here so you can see it, right? Because this is convincing. So again, if you look at this function at -3, you get garbage that comes out of the function. There's nothing meaningful there. But to the left of -3 and to the right of -3, notice you see this clustering of numbers, right? And so if you had this table alone, you would gather that the answer here is -7, but this here presents the analytical way of doing that. Alright, so we're going to move on to one more type of problem. So I'm just classifying these types of problems for you guys. So here's another pretty popular one. Okay. So based on the fact that we're looking at meaningful, challenging problems, right, you could gauge in this situation that if you plug in t equals 0, you run into that same difficulty as before, right? So this is going to give you the 0 over 0 form. And this doesn't mean the limit doesn't exist, right? It just means you can't find it by letting t equal 0, right? You have to find some other way of doing it. So we're going to try this here. Okay, so this is the problem here. So this here is a technique where we can multiply by the conjugate, right, of the numerator expression, and then the hope there is that something simplifies. So I'm going to do that here. Okay, so what are we doing here? We're just taking the exact same expression as we see in the numerator, just changing the sign in the middle, right? And if you look at what's in green, this is just the number 1 in disguise, right? Something divided by itself. And then we're going to do a little bit of the algebra here and see what happens with this limit. Okay, so I'll just repeat this here. This is the limit as t goes to 0. Okay, so the magic, in some sense, happens in the numerator. Nothing too interesting happens in the denominator, so I'm just going to repeat that. Right, with the parentheses. Okay, so here we have two binomials, and we're going to end up with the difference of two squares. So the first two terms we end up with 2 minus t, right? The two middle terms are going to cancel out because they're opposite in sign, and then negative root 2 and positive root 2, we just end up with negative 2. Okay, so you can check some of the algebra on that. And then notice we have 2 minus 2, right? So we have 0 there, and then t over t. We do have to watch that negative sign. So these will cancel out here, but we're left with negative 1 up there. So we're going to clean up this entire expression here. It appears we have negative 1 in the numerator, and then this expression there in the denominator, and then we can figure out how to resolve this problem. Okay, so I'm going to move this, and let's finish this here. Okay, so in the end here, we have the limit as t is approaching 0. We have negative 1 here, and then down here we have this. Okay, so this is like an updated version of what we had earlier, right? So our earlier problem, I'll just flash it right up here, right? This was our earlier problem. We could not solve this problem by letting t equal 0, and you'll notice that this here, if you let t equal 0, that's valid, right? So it's something that you can do directly. So really multiplying by the conjugate here is a way of correcting the function, right? Avoiding that bad point, and then you can calculate the limit. Okay, so you can let t equal 0 directly here, and so you'll get minus 1, and then you'll get root 2 twice, right? So you end up with root 2 plus root 2. So we could just write that as negative 1, and we have a pair of root 2's. Okay? And just like we've seen before, you could check that on a calculator, right, on a table, just to notice that you're clustering, right? You get closer and closer to this value that we see here. So just in summary, right, the first technique we saw was just plugging in, nothing too interesting. The second technique you might want to call cancellation, because we're getting rid of that, that factor there that's causing a difficulty. And then in this third example, we might call it rationalizing. So there are different algebraic techniques that you can use to evaluate limits. All right. So very last thing I want to do here is we have a pretty important theorem here at the end of this section, and I'd just like to do an example to illustrate how it looks like, or how it looks in action. So this theorem is called the Squeeze Theorem, and that name becomes apparent when you look at it. So what we have here is we have three functions at play, and they are related by this inequality, right? So g being the largest and h being the smallest. And so this statement is true for all values of x, except possibly at some point. And then what the squeeze theorem says is that if you can take the limit as x approaches a of both the small function and the large function, if they arrive at the same location, we call it L, then that means there's nowhere else that the middle function could go. So the conclusion here is that the limit of the middle function as x approaches a is also L. Okay, so the tough part, or the reason the squeeze theorem is a little difficult, is oftentimes you have one of these functions, but you have to develop the other ones, right? And to develop this relationship here. Okay, so this is it. We're going to do this example and maybe take a look at things graphically so we can see what's happening. Okay, so this example is a pretty challenging one because if you look at the limit directly, right, if you try to plug in x equals 0, you run into some problems here, right? So this part of the function is not a problem as x is approaching 0, but the sign of 1 over 0, that's not a well-defined expression, and then this function begins to oscillate, right, as x gets closer and closer to 0. So one way I like to do this problem is to break it into components, right? So if you look at the trig part of the problem, right, the sine of anything, so we're going to write this down here, so the sine of 1 over x. It doesn't matter what the output is here, this function is nicely bounded, right? So we know that the range of the sine is between -1 and 1, so regardless of what this is, it has to be trapped between these two numbers. So the other piece of this, if we think about it, x, right, is the other component. So if you just think of x in its own right, you can also bound this function, right? So we don't know the sign of x because x is approaching 0. It could be from the left of 0, it could be from the right of 0. But what we can do is we can create an upper bound via absolute value of x. And then in case this has a negative sign, we can bound it on the left-hand side with negative absolute value of x. So one of these inequalities is going to hold at equality. But regardless of the sign of x, this statement here has to be true. Okay, so once we have this information here, what we're going to do is to just mash these two inequalities together and then come up with this function here. Okay, so I'm going to look at this here and just see if we can write this down. Okay, so we're going to keep the negative sign on the left-hand side. We're going to do some multiplication here. And then here we have absolute value of x. So notice the point, right, or the main objective of this is we're getting the function that we're trying to examine in the problem as our middle function in the squeeze theorem, right? So what we want to do with this function is to determine what happens to it, right, as x goes to 0. Okay, so we have some room here, so I'll get rid of this. And then we'll just finish this up, right? So now if we look at this work here, we're going to let x travel. Okay, so we're going to let x go to 0. And notice the nice thing about the squeeze theorem, the development of these functions on the ends, is if x approaches 0, these two functions are very easy to determine, right, what the limit is going to be. So absolute value of x, that's going to go right to 0. The same thing happens here. This goes right to 0. So the essence of the squeeze theorem is that if the two functions on the ends, right, the larger function and the smaller function, travel to the same location, there's nowhere else that this function could arrive, right? So the conclusion here that we end up with, so we could write this out, the limit as x goes to 0 of x sine 1 over x. This is also 0, right? And it's mainly because this function is squeezed between these two here, so this limit is 0, even though you can't calculate this via direct substitution, right? Because the sign limit by itself is one that doesn't exist. Okay, so this is a pretty tough problem. It's very analytical, but something you can do to convince yourself that it's valid is to use some of the older techniques, right? A table or a graph. And in this case, I'm partial to the graph because it illustrates things, I think, pretty nicely. I'm going to put this graph here. Okay, So if you look at this graph, you can see the individual parts, right? So this little graph on the top you will recognize is this one here, the absolute value function. And then you have negative absolute value function on the bottom. But what you'll notice is the mystery function in the middle, right? This is the one that shows that oscillating behavior. But notice that it stays confined between absolute value of x on top and negative absolute value of x on the bottom. So because both of these functions travel to the same location here, even if this function oscillates like crazy, it's going to have the same limit, right? So the limit here is still L equals 0.